So over the last few weeks, we've essentially had 4 content sessions where we covered all of the content. We then did 2 sessions where we went over common questions, the key concepts and the key calculations. Then we sat the full scale exam and we reviewed it last week. And that brings us to this week, which is the final of 9 weeks, which is the Module 5 review. So this is the last scheduled session for this term, but there are going to be drop-in sessions throughout next week and the week after, where you can come in and ask any questions you have, and I'll just be on the call for about an hour or so each time. So you can drop in, ask whatever questions you have, just one-to-one with me, and then that'll take you through to the day of your exam. Any questions about the drop-in sessions at all? Okay, cool. So we'll spend about 30 minutes on each inquiry question. We'll start with the first one. Very beginning of the module, we talked about how in year 11, you've only seen irreversible reactions and you introduce for the first time reversible ones. This helps to explain static and dynamic equilibria, which answers the question of what happens when chemical reactions do not go through to completion. The first dot point talks about reversibility, where you have 4 case studies, burning of magnesium and steel wool. These are your metal combustions, and they serve as your irreversibility case studies. So make sure you have these as what you give if you're asked for anything irreversible. Your reversible reactions are given as cobalt 2 chloride hydrate and dehydrate. So this is your pink solid turning into a purple one, then a blue one as you heat it, because this removes water from the cobalt chloride hydrate. And then you can also add the water back in to the light blue dehydrate and turn it back into a pink substance. So it goes both ways. And this is the first reversible reaction you see. This reaction, importantly, is not a dynamic equilibria. And I think that's something that I didn't emphasize too much when we went over it the first time because we didn't know what that meant. But when you talk about this case study, this is not dynamic because it only will go towards one of the two sides when you add heat or when you remove water or put in water. If you aren't removing or putting in water, the rate of reaction is 0. So this is not dynamic. The second case study is your iron thiocyanate. So if you react iron with thiocyanate, you form iron thiocyanate. And this is a reversible reaction where if you turn iron and thiocyanate into iron thiocyanate will turn back into the 2 ions at the same time that is happening. So because you have a non-zero rate of reaction with a bit going forward and a bit going back, that then is a dynamic equilibria where the rates become equal at some point. Okay. Any questions on the first 4 case studies? Just as a quick overview. And throughout today, make sure any questions, just ask them. Okay. Second inquiry question, or second dot point in the first inquiry question, talks about static and dynamic equilibria and open closed systems. You should know what a system is. A system is just any chemical reaction. Everything outside of that reaction is surrounding. And when we talk about energy transfer in any reaction, when a reaction is either endothermic or exothermic, it is talking about a transfer of energy from the system to the surrounding or from the surrounding to the system. And oftentimes, when we talk about temperature change in a reaction, are we talking about temperature change of the system or temperature change of the surrounding? Because they're very different things. Say if you said an exothermic reaction will increase temperature, is that talking about the system or the surrounding?
The surroundings?
Surrounding. Good. So oftentimes, temperature change is just describing the surrounding. In an exothermic reaction, energy transfers from system into the surrounding, and that would cause an increase in the temperature of the surrounding. Okay. Then open and closed system, we should know a closed system is one where you have transfer of energy only between the system and surrounding, or the system and surrounding, with no transfer of matter. And having a closed system is a criteria required to form static and dynamic equilibria. You can only form it in those two contexts. An open system, on the other hand, is where you have the exchange of both matter and energy in and out of the system. Open system cannot reach static or dynamic equilibria because if you are constantly removing matter, you will never reach a constant amount of matter as reactant and product. So you cannot form equilibria in an open system. I think one final important case I'll bring up with the closed systems is if you have any solution with ions in it, we consider solutions to be closed systems, even if they are exposed to the atmosphere. Okay. Any questions on open and closed systems? Okay. So the big question we answered at the very beginning is what actually is equilibrium? Equilibrium is a state where concentrations of reactants and products are constant, and on top of that, the rate of forward and reverse reactions are equal. And those keywords, equal and constant, meaning different things. So the two types of equilibria you see are your dynamic and static equilibria. Dynamic equilibria is where you have non-zero rates of reaction. Static equilibria is where you have rates of reaction that are zero. And that is the big difference. It's about the reaction rates, either being in flux, which means non-zero, or constant, which is zero. Which really, yeah, I don't really like the word constant. It really should say zero. A dynamic equilibria never reaches completion. It only goes partially towards completion, whereas a static equilibrium will reach completion. And that's why it reaches completion, the reaction stops proceeding, and hence that is a zero rate of reaction once the reaction is completely finished. Dynamic equilibria therefore has to be reversible. Static equilibria typically forms from non-reversible reactions. They have the corresponding arrows that you see here, and an example is given at the bottom. Okay. Any questions on equilibria, dynamic or static? All right. Once you then know what static and dynamic equilibria are, you should be able to model them. So you can create a dynamic equilibria by exchanging objects from one container to another and from the other container back in differing proportions. And eventually, in this case, we were transferring half from A into B and then a quarter from B back into A. Eventually, you would find that the rate of exchange becomes constant once you reach certain concentrations. Sorry, the rate of exchange becomes equal once the concentrations reach a certain amount. And from there, the concentrations stay constant and the rates of reaction stay equal and constant. If you've been given a different example to model dynamic equilibrium from school, you are more than welcome to use that at school, of course. But this is just the simplest one that I typically teach. Anyone have any other models that they came up with at school?
In our class, we did like a paperclip one where you like join paper clips into like two and then like take them apart.
Nice. So it's similar effect, like you were joining like half onto one and then removing some from the other. Okay, cool. So generally speaking, this is what it'll look like beware if it comes up in the exam, but dynamic equilibrium model. Cool. These two diagrams are particularly important. In your exam, you can be asked to draw a diagram that represents a static equilibrium or draw a diagram that represents a dynamic equilibrium or even both. In this system, you're shown white dots that react with black, I'll call them atoms. White atom reacted with black atom to form a white and black atom attached as a molecule. In a static equilibrium, you show the reaction goes to completion. This implies, in this case, that 1, 2, 3, 4 molecules are formed, consuming 4 of each atom. And that leaves over 2 black atoms as excess. So this reaction would have gone to completion in this diagram. If this was the case, that would mean the forward reaction is now 0. And because the reaction is irreversible in static equilibrium, you are not reforming any reactant. Hence, that's why you have no white atoms left. Thus, because the rate of forward and reverse reaction are both 0, this is a static equilibrium model drawn as a diagram. Any questions on that there? Okay. So then in the other example, if you're instead showing it as a reversible reaction, where white and black combine to make a white and black atom attached to the molecule in a reversible reaction, this is where you're showing that 2 of each atom have reacted to form 2 molecules, and you have a bit of reactant and a bit of product left over. This implies the reaction went to partial completion. It has not gone the whole way. So while some of the joined molecules turn back into reactants, you constantly have reactants that are turning back into molecules as well. And that constant exchange at a non-zero rate is modeling dynamic equilibria instead. Obviously, these models have significant limitations because it's just a snapshot. It's just a point in time, but this is what they typically expect when they ask you to draw a model in your exam. Okay, any questions on those two? Cool. We then move into non-equilibrium systems and Gibbs free energy. So you have the dot point asking you to analyze examples of non-equilibrium systems in terms of the effect of entropy and enthalpy, for example, combustion and then photosynthesis. So you should now know enthalpy is essentially the kinetic energy, the heat energy of a system, and it's used interchangeably with heat. We measure it in terms of joules per mole or kilojoules per mole. And we can talk about reactions either through, in terms of the enthalpy drive, which is telling you for a particular enthalpy, is the reaction becoming more spontaneous or is it becoming less spontaneous? We'll link that to Gibbs' equation in a second. The second thing you should be aware of is entropy. So entropy being the number of possible microscopic configurations of a system or how disordered the system is. Again, it can be measured in joules per mole per Kelvin or kilojoules per mole per Kelvin. But the important thing, as I've emphasized many times this term, is whenever you perform the Gibbs calculation, you must match the units. So if you process enthalpy in terms of joules, you process entropy in terms of joules. If you process it in terms of kilojoules, you process the other in terms of kilojoules. So just make sure you make that conversion if you ever do a calculation and they give them as different units. Okay. Just to be sure we have this covered, entropy, there are various things that can affect the entropy of a system. What are the things that can affect entropy? What can increase entropy? There's a few factors. How can we increase entropy?
Changing the state.
Good. Changing the state. So gas being the highest, then aqueous and liquid, followed by solid. Great. There's three others, I believe. So it says state. What other factors can we modify?
One of them is the amount of moles being produced. If more moles, I think,
Great.
are
If you
being
have more
produced.
moles, exactly. If you have more moles, that means there's more things in the system, more things to order, and so the system is more disordered. So more moles or higher concentration, if you want to consider it that way. Okay, two more. What else can increase entropy?
An increase in temperature.
Increase in temperature. Good. Because particles move faster, again, harder to order because they take up more positions per second. And there's one final one. What's the last thing that increases entropy? Think about the container.
Decreasing volume.
Decreasing volume would
Oh,
actually make things, yeah. So decreasing volume would put all the molecules in a smaller space and mean there's less places they could take up.
oh, okay, then
Right?
increasing volume.
Yeah, so increasing volume is actually what's going to increase entropy because now you have more possible combinations.
Mhm.
Does that make sense? Very good. So increasing volume or decreasing pressure. These are the four factors that change entropy. Whilst I don't think it'd come up, still good to understand what's driving entropy high or low. Okay. And similarly, entropy drive can either be forward or reverse. And as we know from the Gibbs equation, there are three factors that affect spontaneity. Delta H, T, and delta S. Delta G is spontaneous when it is positive or negative. It is spontaneous when it is negative, of course. So for delta H and delta S, they can either drive the reaction forward or backward, and you should be able to confidently discuss when this is the case. Whatever contributes negatively to delta G will drive spontaneity. So if delta H is negative, it means delta G is equal to a negative number being contributed in minus whatever temperature times entropy is. And so in this case, if delta H is negative, it is energetically or enthalpically favorable. It means it is an enthalpy drive that is forward enthalpy drive. Or vice versa, if you have a positive delta H, this is instead energetically unfavorable because it contributes a positive number to delta G. Delta S is a little bit more tricky just because of the negative sign in front of T delta S. So when you consider entropy's drive, you consider the whole minus T delta S unit. If delta S is positive, this whole unit is a negative positive number. Hence, it is a negative number. And so a positive entropy contributes a forward entropy drive. It is entropically favorable, whereas a negative entropy contributes a positive number and is entropically unfavorable. Okay. Any questions on entropy and enthalpy drive?
Wait, so sorry, you're saying for the column of pluses and minuses under the negative T delta S, are
Yeah.
you saying that the plus is if the entropy is negative?
The plus is if,
Or is the plus and the
oh
minus
yeah,
referring to the actual entropy or the minus T delta
good
S?
question. The plus and minus in this diagram is representing to just the entropy alone. So
Okay.
it's saying if you have a positive entropy, it is going to contribute negatively.
Yeah, okay. All
And
right.
hence be entropically favorable. Yeah, good question. So the only tricky cases here are the bottom two. In the top two cases, if you have a negative delta H and a positive delta S, you'll always have a negative delta G. And in the second case, if you have a positive delta H and a negative delta S, you will always have a positive delta G. The bottom two cases become tricky because it can be either, depending on what temperature your system is at. So you should be able to negotiate when is the reaction going to become spontaneous or when is it going to become spontaneous? That was one of the questions we asked in the exam from last week. And does anyone remember when that's the case? When does the reaction change from being spontaneous and non-spontaneous?
When Gibbs free energy is 0.
Good. So when delta G equals 0, this is the middle point between delta G being either positive or delta G being negative. And this is where your reaction is changing from either non-spontaneous to spontaneous. So if you're asked to calculate that, the question is typically, well, what temperature does this system change from spontaneous to non-spontaneous? And if you know delta G is 0, and delta G is also equal to delta H minus T delta S, a very common question you'll get is then to solve this and find that delta H equals T delta S, and therefore T equals delta H on delta S. And that's your temperature at which the reaction changes from spontaneous to non-spontaneous. Does that make sense for everyone? Okay. One small thing to note is for any reversible reaction, your delta H, delta S, and delta G for the reverse reaction will just be the same number, but with a negative sign in front. So if your delta S was negative 4087 in the forward direction, it would just be positive 4087.8 in the reverse direction. And this is true for delta S. This is true for delta G as well. It's just the negative version. There are two important case studies. And for reference, whenever I say case study, it's something that's listed in the syllabus and you should memorize it, annoyingly. But if you understand why it's true, then you don't have to really always memorize. Combustion and photosynthesis are the two non-equilibria systems that we have to know. Combustion refers to the burning of substance in oxygen. It has a negative delta H, a generally positive delta S, and therefore its delta G is negative, since a negative minus a positive is always going to be a negative number. For photosynthesis, the reaction is as follows. Some of you may do bio and will not already know this, but photosynthesis becomes an increasingly important equation. I mean, it's one to just have for this module. So if they ask you to write the equation for photosynthesis, you should have something ready. The delta H is positive because it's endothermic. The delta S is negative, and so the delta G overall is instead positive, going the other way of combustion, meaning it's a non-spontaneous reaction. So those two case studies, I would remember those. Okay. Now, delta G in equilibria is slightly different. Delta G is at equilibrium if it is equal to 0, or in some cases very close to 0. What this means if delta G is at 0, it means the reaction is slightly spontaneous in the forward direction, slightly spontaneous in the reverse, so much so that it can proceed in both directions. And this would be the exact point where delta H equals T delta S, more or less. Okay. So at the very end of the first inquiry question, we talk about collision theory explaining that in any successful reaction, you have particles colliding, and when they collide with sufficient energy and the correct orientation, they will successfully collide. The more of these successful collisions you have per second, the faster the rate of reaction, and you can discuss why rate of reaction changes in terms of these successful collisions. There are 6 factors that affect your collisions. Concentration, volume, pressure, and surface area only affect the frequency of collisions. So if you change any of those, it means that the particles collide more times per second, and that leads to higher successful collisions per second. On the other side, catalyst is the only one that only affects success rate. And you can justify the success rate as a higher success rate, meaning a higher proportion of particles over activation energy. A higher proportion of particles over activation energy is really what is causing a higher success rate of collisions. And we can justify that using the Maxwell-Boltzmann curve. So the Maxwell-Boltzmann curve on the x-axis shows the kinetic energy of particles. On the y-axis, it shows the number of particles. And this is a normal distribution, showing the number of particles at each kinetic energy value. For any reaction, you have some activation energy, such as this one here, shown in green, AE being activation energy, and a certain number of particles are over that activation energy, and they can successfully collide. So what happens when what happens when we add a catalyst to the system? How does that push more particles over activation energy?
It moves the curve to the right.
Almost. Say that one in a minute's time. A catalyst. What does a catalyst do?
It makes activation energy lower, so it moves
Good.
the that way.
Great. So the activation energy is what changes when you add a catalyst. It shifts it to the left. Activation energy with a catalyst shifts this activation energy to a lower kinetic energy level. And that now captures this whole new range of particles, which are now over activation energy. And hence you now have a higher proportion of particles over activation energy, meaning each collision is more likely to be successful. Happy to explain that again. Anyone want another explanation? Any questions? Sophie, all good? Okay. So this is your catalyst case. This will reduce your activation energy, push more particles over that activation energy, and so your reaction proceeds faster. What about temperature? What happens there, Echo?
Yeah, then the curve shifts to the right.
Good.
Everything has more energy.
Exactly. So if you increase temperature, that's the same thing as saying I'm putting more kinetic energy into my system. And so your curve is effectively going to shift to the right. And what you're doing is you're pushing a significantly larger number of particles over that activation energy initially, which causes a higher proportion of particles to be over activation energy and hence faster rate of reaction. So temperature is the other factor that affects success rate, and those are the harder ones to explain. Temperature at the same time does increase frequency as well, because if your particles are moving faster, you're also going to be colliding more frequently per second. Okay. Final thing we talk on is how you can link collision theory to the concentration and rate graphs. For any shift in equilibrium, the crux of why you shift is because the rates are no longer equal. That happens in every shift, whether it is a concentration change, whether it is a temperature change, whether it is a pressure volume change. The reason why your shift happens is because your forward and reverse rate are no longer equal. So they're not equal for any shift. In this case, the forward rate is higher than the reverse rate. And it's because, in this case, we have a fair amount of reactant and very little product. Lots of reactant means lots of reactant collision, meaning a high forward rate, whereas a low product concentration, in fact, a zero product concentration, means no product collisions and a zero reverse rate. So as the reaction proceeds and your forward rate is happening, this causes you to form some product as the forward rate proceeds, and it consumes reactant. Because the reactant concentration drops, the forward rate drops because there are less collisions per second, and because the product concentration increases, the reverse rate now becomes non-zero and increases up. And then as the two reactions continue to proceed, eventually you get to a point where the rates equalize and the reactant concentration stays constant while the product concentration stays constant as well. Okay. Any questions there? Emily, question?
This might be stupid, but is when they're equal, is it always like directly in between the forward and reverse rate?
Oh, yeah, fair question. No, it's not. No, it's not. So for like simplicity, they're shown like right in the middle here. But sometimes the change in rates can actually be like dependent on the stoichiometry.
Okay, yeah.
But for our purposes, it's somewhere in the middle. And that's really all we need to know. There's one question I gave, I think in the paper, that might have been somewhere in the middle it was like slightly on one side as opposed to slightly on the other side. Is that the question you're thinking of?
Yeah.
Yeah. So for that one, and I'll bring up the paper. Oh, I think it was in the key concepts. I think it was not this one. Oh, is it not here?
I've seen it. I don't know where I've seen it, but I've seen it before. I just wanted
Yeah,
to
I know the one you're thinking of. I'm just not sure where I had it.
Mm.
But anyway, the point in that one was there was a slight difference in stoichiometry. So you were forming, I think it was like more product compared to more reactant or something like that. And so if you're forming more product, the reverse rate should increase at a faster rate compared to the reactant coming down. Does that make sense?
Yeah.
Yeah. Okay. And that brings us to the end of the first content session. Going back quickly, very quickly over, we talked about irreversible and reversible reactions, equilibrium types, open and closed systems, Gibbs free energy, modeling equilibria, and then at the end we touched on collision theory and how that results in equilibria forming. Any questions going back any of that? Okay. We'll go through the second inquiry question as well, and we'll have a break after this one. So factors that affect equilibrium. Inquiry question is, what factors affect equilibrium and how? And we now know that equilibrium is a careful balance, almost, of forward and reverse rates and a certain concentration of reactant and product. You can change this when you change any of concentration, volume pressure, or temperature. And you can predict those changes through Le Chatelier's principle or explain them through collision theory. You need to be able to do both types of explanation when you write them in your exam, and they are different. Can anyone quickly summarize? How is LCP different to collision theory? How do you justify those being different responses?
LCP tells you which way it's shifting, but it doesn't tell you why, and then you can use collision theory to explain why it's shifting that way.
Correct. And then how do you justify using LCP? I'll throw this one to Sophie. Do you want to have a go? How do you justify using LCP to justify shift?
The reaction goes against the disturbance to try and counteract it.
Exactly. Good. And that discussion, do you ever mention rate of reaction in an LCP response?
Um, no.
No, you don't. Good. So you should never ever mention rate of reaction in any LCP response because you mentioned that in collision theory. Your collision theory responses are all based in rate. Your LCP responses are all based, as Sophie said, in resistance and how you're counteracting a change. They are entirely independent, so please don't mix them together. LCP, to quickly rehash, every time you define this for the first time in a response, I would define this if it was up to me to play it safe. You would say system at dynamic equilibria, if disturbed, will shift to minimize or partially counteract the change until a new equilibrium is reached, or some paraphrasing of that. It helps to predict the direction will shift, and you can either go to the right or to the left. When we say shifting to the right, we refer to the system shifting to make more product. And this explanation is in terms of collision theory, just to be clear, because if you're talking about rate, that's going to be a collision theory point. Or if you're shifting to the left, it means you're going to form more reactant and decrease your concentration of product. So understand shifting right versus shifting left. Any questions to begin with? LCP, shift right, shift left? Okay. So every LCP response, the easiest structure to follow is disturbance, resistance, shift. You identify what disturbance happened. Did you change concentration, temperature, pressure, or volume? Then you say how you would counteract that. So if you increase the concentration of a reactant, the resistance is going to be to decrease the concentration of said reactant. And you'll shift either right or left in order to do that. So if you're trying to decrease the concentration of reactant, that's going to be a shift to the right because the reaction will consume reactants. Disturbance, resistance, shift. One small thing to note is with concentration changes, say that you increase the concentration of nitrogen in this system, the resistance will never ever nullify change. Nullifying meaning bring back to where it began. And it will never exceed the concentration that you started at either. That's not possible. Resistances of concentration changes are only ever partial counteractions. So you'll end up somewhere between the maximum concentration and the starting concentration. It will never go below or be the same as the starting concentration. Okay. Is everyone happy with the pace? All good? Gabriel, you right? Okay. So all the LCP shifts that are possible are on this page. If you were to change the concentration, the shift will shift to decrease that concentration. And it just goes the opposite way. If you add or remove a solid or pure liquid, this is the examiner's favorite trick, probably the most common one. This will have no effect on equilibrium if you add or remove pure liquids or pure solids, because they are not included in the Q expression. So they don't create a difference between Q and K, as we'll talk about later. No effect. Another tricky one is if you were to add a solvent to a solution. If you add a solvent to a solution, what I mean by this is imagine you had an equilibrium system within a beaker, which is water. If you now add more water into that beaker, you've now increased the volume of that solution. And so adding solvent to a solution equilibria is the same as saying you're increasing volume, and hence this decreases the concentration of all the substances within. And you think of this the same as like a volume increase for a gaseous system. Adding a solvent increases volume, which decreases the concentration of everything, and therefore you will shift towards a side with more moles in order to bring the concentration of everything back up. This one's definitely a rarer case, but still possible that they ask. Any questions on those three to begin? Okay. Temperature changes are relatively intuitive. If you increase temperature, the system will shift to try decrease temperature, and it does so by taking heat in. So it proceeds the endothermic direction, because the endothermic direction consumes heat. It takes heat into the system and out of the surrounding. Conversely, if you decrease temperature, the system will shift to the exothermic direction, because the exothermic reaction releases heat and hence increases temperature back up to resist that change. Pressure volume changes. Partial pressure as an important concept, you think of the same as a concentration almost. It's the pressure if that was the only gas in the system. The pressure if that was the only gas in the system. So when you say you increase the partial pressure of a gas by pumping in more of one gas, that's in your head the same thing as saying I increase the concentration of a substance in solution. And so the system will shift to decrease the concentration of that specific gas. This is different to saying I increased the total pressure or I decreased the volume. In that case, where you increase total pressure or decrease the volume of the system will shift to favor the side with less moles. So if it was increased total pressure, you would shift to side with less moles, because this brings back down your pressure. Brings your pressure back down and hence resist the change. The final two cases are your inert gas cases. What's inert gas, just quickly?
Like non-reactive.
Great. A unreactive or non-reactive gas. So it's not going to interact with your equilibrium system. If you add this into a box that does not deform, there will be no effect on equilibrium. And if you add it into a bag, which expands when you add that gas in, this is the same as saying you increase the volume of the system. And that will then shift towards the side to increase pressure back up.
So in a question where they use that with an inert gas, they'll have to specify what container it's in.
They really should. They really should. In the case where they don't, they typically are referring to the rigid box. If they don't, they're typically referring to the rigid box, which is annoying, but they should specify which of the two cases they want you to talk about. Yeah. Okay. Any questions on the pressure volume cases? Other than that. Okay. Final thing here is catalysts. Catalysts have no effect on the position of equilibrium. No effect. So if you add catalysts, you'll still reach the same concentrations when you reach equilibrium, but you reach equilibrium a little bit quicker because you have a faster rate of forward and reverse reaction. There are 3 case studies given to you for explaining LCP shifts. These 3 cases, if you wanted to go above and beyond, you would remember the equations, you would remember the colors of the substances, and you would remember the enthalpy change. This is like your final 5%. So if you've done 95% of the content and like you're just looking for that final 5% of coverage, spend some time on this. But I wouldn't say this is the highest yield to remember each of the 3. Okay. So that's LCP. Collision theory and justifying responses. We'll take a break after this. As we said, collision theory talks about successful collisions per second, and that can be changed either through frequency of collisions or success rate. In other words, proportion of particles over activation energy. Each change in condition, whether it's temperature, concentration, or pressure, shows a different concentration change. And this is how you identify them on the graphs that you'll see in your exam, which are very common. A temperature change shows no sudden change in concentration. No sudden change in concentration. A concentration change shows a sudden concentration in one of the substances and none of the others, because you are adding in something into the system. So a concentration of one substance changes, or you're removing one substance, and so the concentration of that one substance changes. And finally, a pressure change or a volume change will change the concentration of everything in the system in proportion. If you were to halve volume, that would double the concentration of everything. And you can justify why the rates will then change the way they do in terms of collision theory. When you structure your response for collision theory justifications, you say what disturbance happened and how did it change forward and reverse rate. It may just be one of them too, but for pressure, volume, and temperature, you change forward and reverse. For concentration, you only change one of forward or reverse. In the case of a concentration justification, or actually the response structure first, you talk about which of forward and reverse rate changed, compare whether forward is higher than reverse, and then because you know, say for example, forward rate is higher than reverse rate, it means the reaction must proceed in the forward direction, and hence the equilibrium shifts right. So 3 stages once again to explaining collision theory. For concentration, in this system, you see nitrogen increase in its concentration. That meant that the concentration of reactant, which in this case is nitrogen, has increased, and hence the forward reaction rate increases because there are more frequent collisions. That creates a difference in forward and reverse rate, which causes the system to shift to the right as the forward rate proceeds more than the reverse. And eventually you reach a point where the rates equalize. And that's your concentration shift. A bit more detailed there if you want. Any changes in the concentration shift first? Pressure volume. You see that if you were to decrease volume, all of the concentrations go up in the same proportion. You see that both forward and reverse rate actually do increase. So there's an increase in the reverse rate and an increase in the forward rate. But the forward rate increases proportionally more. In this case, because there are more reactant moles, I'll write that out, more reactant moles than product moles. And so the side with more moles is affected by the change proportionally more. Affected by change proportionally more. And then because the forward is higher than reverse, the reaction shifts right, and eventually you reestablish equilibrium at a point where rates are equal again. Pressure volume. Any questions there? Okay. Finally, temperature change. As you can see here, with temperature change, you see no changes in any of the concentrations when you make the change. There are no changes in concentration. That's your telltale sign it's a temperature change. You also see that both forward and reverse rate actually increase. Both forward and reverse rate increase because you now have a higher number of collisions per second in both the forward and reverse reaction, and the success rate is higher in both the forward and reverse reaction. But in this case, the reverse reaction increases by slightly more. This is because the reverse reaction is an endothermic reaction, whereas the forward reaction is exothermic. And temperature change affects the endothermic side. Change in temperature affects endothermic side proportionally more. And some schools really want you to mention the words activation energy. When you say temperature change affects the side with higher activation energy proportionally more. Temperature change affects the endothermic or side with higher activation energy proportionally more. And so here, that creates a separation in rates again. The reverse rate is now higher than the forward. When the rates come back together, this is because the reaction has proceeded to the left in the reverse direction, and hence equilibrium shifted left in this case. And we can always justify that through Maxwell-Boltzmann if we wanted to as well. Any questions on the temperature change? Okay. Final two enrichment cases, if you want to go through them as well. They're written there, the inert gas case for fixed volume and fixed pressure. So to summarize, you should know that concentration change looks like a sudden change in concentration. Pressure volume is sudden concentration change in all of the components, and temperature change has no sudden changes in any of the concentrations. The only other thing I'll get you to consider is when you make a pressure volume change, the proportion of change should be reflected in the sudden changes. So this graph is actually slightly wrong. There's a slight mistake, in my opinion, on this part of the graph. they're showing that the pressure change is all the same. Like, sorry, the concentration change from the pressure change is all equal. But this is not the case. You should expect to see that the concentrations actually all change in proportion. So if NH3 increased by this to me looks like about a 50% increase. Does everyone agree with that? So you would expect the same proportion of change to NH3. You should expect this to actually go up by the same proportion of, say, 50%, and this N2 to go up by 50% before your before you reestablish equilibria. So just keep that in mind when you draw your graphs of pressure and volume change. And actually, one more thing I'll add on. It is then after this sudden change where everything is in stoichiometric ratio. So the reestablishment of equilibrium, this should all be in stoichiometric ratio. If it's 1 to 1 to 1, then everything should be the same. If it's 1 to 2 to 3, it should be in a 1 to 2 to 3 ratio for each change.
I have a question, sorry. With the 50%, do you mean 50% of what it was like just before the increase?
Correct. 50% of what it was just for the increase. Because if we put numbers to it, say that the concentration here was 3 molar. This was, for simplicity, just accept these numbers, 1, 2, and 3. If you then halved the volume, right? What would you expect to happen to all the concentrations?
Double.
They all double. It's not like they all go up by 1 molar,
Okay, yeah.
right? They all change in the same proportion. It's a good question. Anyone else have any questions? Gabriel, Echo?
This was like just about the responses for like collision theory in general.
Yeah.
So like when you write it, it's like for the steps, it's like you establish like what happens with the rates like initially, and then like at the end, I was wondering, do you have to say how like after one has increased, then the other one has to like kind of like catch up? Because yeah,
As in, like, once you've established there's a difference,
yeah.
do you need to then say what happens after? Is that what you're asking?
Because I feel like I might like over explain it too much, but I'm not sure.
Yeah. So best practice is you establish there's a difference of rates.
Yeah.
And then part of explaining this final thing of equilibrium shifting, if you wanted to be very thorough, you would go and say equilibrium shifts, say, to the right.
Yeah.
Which means that the forward rate decreases whilst the reverse rate increases until they reach an equal rate
Yeah.
and reestablish equilibrium. So it is probably, I would say it is important to discuss what happens to the rates as you reach equilibrium, but
Yeah.
don't overkill it, as you say. You don't have to like really go into the very nitty-gritty and do like one step, then it moves, and then again and again, because that will take up too many words. Just keep it like broad. Describe what happens overall and that you do reach rates that are equal eventually.
Okay.
That makes sense?
Yes.
Okay. Sophie, any questions? Okay. Cool. Some sample responses here. So this is the way I'd more or less structure the responses. You can obviously add a bit more detail. These are the bare bones of what you're expected to write. But then you would adjust based on criteria that you read as well and add in things as you see fit. So to summarize, we talked about LCP and collision theory, separate responses, LCP in terms of resistance, collision theory in terms of rate. We then also mentioned the different factors that can affect equilibrium, which are concentration, volume pressure, temperature, and inert gas being added in. We also talked about catalyst having no effect on equilibrium position. And we looked at the various graphs for concentration, pressure, and temperature change and what they should look like. Okay. End of the second inquiry question and halfway through mod 5. So we'll take a 5-minute break here and we'll get into the third inquiry question. So I'll see you back at 8:12. Get a drink of water, come back, and we'll lock back in to finish off. Okay. Start coming back now. Get started. Okay. Just out of interest, is everyone finished with Mod 5 at school in terms of the content itself? Emily, yes. Sophie, where are you up to?
We're up to this inquiry question.
Okay.
Yeah.
Still a fair bit to go.
Yeah.
What about you, Gabriel?
We're starting 5.3 tomorrow.
Okay, fair as well. And Echo?
We're like finishing KSP now.
Okay, cool. So does that mean for Sophie and Gabriel, is your assessment only covering part of Mod 5 from your understanding?
Yes, that's right.
Only up to 5.2 or in 5.3 as well?
Yeah, 5.3 as well.
And Sophie?
I think all of it. I'm not sure.
Yeah, ours is 5.3 as well.
Okay. And are you feeling confident on 5.3 having done it with us? Is that okay?
Mhm.
Gabriel?
Yes, very
Okay,
much.
great. So other than that, there's obviously two inquiry questions left. Gabriel and Sophie, if you do have to head off a bit earlier, if you want to just catch up other study, more than welcome to skip 5.4, but we'll go through the rest of it anyway. So 5.3, calculating equilibrium constant KEQ, basically asks how can you find equilibrium position and what does the equilibrium constant represent? The first thing you learned was how to actually write an equilibrium expression, which is the product concentrations divided by reactant concentrations. And when you write the precise expression, you take each of the concentrations of the product or reactant to the power of their coefficient. And you do that for each one. You only include concentrations which are gaseous or aqueous, and you never include pure liquids and solids in your KEQ expressions, your equilibrium expressions. What is essential to understand, first of all, with K is what does a big K value represent and what does a small K value represent? We should now know that a very big K means that our product concentrations exceed our reactant concentrations. And so you would have a reaction if it was reactants going to products. You would have an equilibrium system which shifts far to the right, meaning you have lots of product and very minimal reactant. That's the case of a large K. In the case of a small K, and for reference, small K meaning K less than 1, big K meaning K that is greater than 1, generally speaking. But like, it can be a range. So K that is much less than 1 would be a very small one. If you have a small K, it means that your system has lots of reactants in it. So it has shifted far to the left, meaning there's very little product and lots of reactant, hence a small K. If you have a K that's close to 1, and generally speaking, 0.1 to 10 are like medium K values where the concentrations are somewhat similar. It means you have similar concentrations of the two. And it's always dependent as well because you have the indices of the concentrations to consider as well sometimes. So it's not as straightforward as, oh, your K is 10, so it's always going to have more products than reactants as a concentration. It may not in the case of the powers playing a role in it as well. So just consider that as well. But for the most part, they'll keep it simple. Two important examples, if you have water or any liquid, you don't include it in your KEQ, or if you have a solid, like lead phosphate here, you don't include it in your KEQ, or as we know now, this is a KSP. Okay. So the first question type that you'll see here is just writing equilibrium expressions. These questions we did earlier. And the second question type is just subbing into a KEQ expression. So when you write an equation, form the expression, and then substitute in the values to find your K. Those question types are relatively straightforward. Then you introduce Q and perform calculations to do with K and Q. To do these, an icebox is required. An icebox starts with an initial, change, and then an equilibrium concentration as the three parts you go through. Your initial concentrations are what's given in the question stem. They'll tell you how many moles or what volume you have. They may even tell you the exact concentration. And if something is not mentioned in the question, their concentration starts as 0. The change is how much the concentrations change by before reaching equilibrium, and the equilibrium concentrations are at the end. Depending on the question, you'll be given a different combination of these variables. You may be given only initial concentrations and asked to find the equilibrium concentrations. You may be given some initial concentrations and an equilibrium concentration and asked to find the K. So there's different questions you can get, and we'll go through those again too.
I just have a question about the icebox.
Go for
In
it.
class, our teacher was like very he like said that we should do it with moles, like number of moles, and then I asked him if we can do it with concentration because me and my friend who also do like tutoring have learned it with concentration. He was like, it gets really complicated when you do it with concentrations. Just like I'm just checking, it's like fine to do it with concentrations for like forever.
Yeah, so from my view, it's fine. I don't think it's more complicated. I would actually argue it simplifies the KEQ substitution.
Yeah.
It's really dependent on the question. So if they give you a question that's in terms of moles, then yeah, go for it. Do it in terms of moles and then convert into concentration at the end, if you wanted to do it that way. At the same time, you could still just turn the moles initially into concentration and then process
Yeah.
it all as concentration.
Yeah. Yeah.
Where I would say definitely don't do it in terms of moles is if they give you concentrations in the question to begin with. That makes no sense because you're
Yeah, he
changing.
was like converting them into moles and then putting them into the thing, which I
Right.
found.
Yeah. In my view, that's more inefficient and you'll be wasting time.
Yeah.
If it's your teacher, they're probably catering to those who are just starting out. If it's like the first time they taught it, but if they're sticking by it, it may be like annoyingly the way they like to mark internally. So just make sure with them that they are happy that if you have the correct concentration in your ICE table and you get the right answer, that they're not going to take marks. Just
Yeah.
really clarify that with them.
Yeah.
But does it make sense the difference between the two cases that I gave as well?
Yeah.
Yeah, and I agree with you. So yeah. Okay. First question type, using an icebox to find KEQ. You can recognize this question because they give you initial concentrations and they give you one equilibrium concentration. Then they ask you find the KEQ. It's just a matter of inserting in the initial concentrations, inserting in the equilibrium concentration, finding the change, using the stoichiometric ratio of the equation to find the other changes, and then finding the end concentrations by using the changes. Once you find the equilibrium concentrations, you can put them into your K expression and you have whatever number it'll be. So nothing too complicated with this first question type either. Any questions on this one? Cool. So second question type here. Actually, just before we move off, let me see. Yeah. So this is a case where I'd say doing it in terms of moles is actually like maybe logical because they give you everything in terms of moles and at the end they convert it into concentration. But if it's not given to you in moles, I wouldn't convert into moles. Second question type, a little bit more difficult. Using an icebox to determine equilibrium concentrations. You now need to introduce something we refer to the small change assumption. So small change assumption is where some unknown change is so small compared to a concentration that you may as well call it negligible. And this helps you to avoid quadratics, cubics, and difficult calculations that you don't need to do in chem. You can only apply this when the KEQ is very small. And this is, I think, the hardest part for people to understand. Why does it matter that your KEQ is small to apply small change assumption? Can anyone try justify it or anyone have an idea as to why that's the case? Why does a small KEQ permit the small change assumption? Yeah, Gabriel?
Is it if KQ is larger, then it would no longer be negligible, and then doing it with small change assumption or just calculating it normally would be entirely different.
Yes. But think about why the small change assumption works when you have a small KEQ. First of all, when you have a small KEQ, what does that mean in terms of product and reactant concentrations?
It means there's more reactants
Good.
significantly.
Correct. So you have a very small product concentration and a massive reactant concentration. And in the case of an equilibrium, it means that if you only had the reactant to begin with, you only proceed a very tiny amount into products, right? So
Yep.
this is your change. This is X, a super small conversion from reactant into product. That's the case where you have a really small K. A very small K means you form very little product, and hence your change is very small. Does that make sense for everyone?
Oh yeah. Yep.
So then if your K is so small that this change of X or 2X when compared to a much bigger number, you can say that that X is very small. That's what we mean, relating it to K. But say, as you said, Gabriel, you have a very big K. Very big K. It doesn't work anymore. Because if you had a big K, that's the case where now you have a massive product concentration and a very small reactant concentration. So the change is instead very significant. And compared to the bigger concentration, now it is significant in the case of a big K. Any questions there?
Would you, when you're using the small change assumption, would you say, um, like change is negligible as the KEQ is really small?
Correct. You would write that right after you apply it, or
Okay.
like inside of it.
Mm-hmm.
So that's all you need. Just justify it when you do it. Correct. Something like this. Assume that X is very small compared to this, and I'll just go a bit further and say because, as you said, KEQ small, significantly small. And typically being significantly small means that your KEQ is less than 10 to the negative 4, typically speaking. Okay. So then going back to the question type, the question stem will give you the initial concentrations. It won't give you any equilibrium concentrations, but it will give you the K. When you take the initial concentrations, you put them into your icebox, and then you suppose the changes occur in terms of X. And these will occur in stoichiometric ratio. So NO changes by 2x because it has a 2 in front of it. Cl2 changes by x because it only has a coefficient of 1. And so you make 2x and x Cl2, and the change in NOCl is minus 2x because of its coefficient of 2 as well. Meaning that the equilibrium is actually 1.0449 minus 2x. But because the KQ here tends to negative 6, very small number, it means that the change of going from reactant to product is so small that you can basically consider 1.0449 minus 2x to be the same as 1.0449. And that's your small change assumption. You always apply it on the number that is being, on the x that is being added or subtracted. It is never applied to any of the freestanding x's, your small change assumption. It's always the one that is being added or subtracted. Okay. From there, you now have your equilibrium concentrations. You insert them into K, solve for X once you equate it with KEQ, or KSP as we'll do later. And that allows you to find X. Then define the concentration of an equilibrium of a substance at equilibrium, you relate it in terms of X, whether it's X or 2X. You can just write out the final concentration in terms of that. Okay. Very common question type. Similar to what we'll do in, somewhat similar to what we'll do in the common ion effect later. Any questions here? Okay. Q. So Q is really interesting because it helps you determine where your equilibrium lies. Is it at equilibrium? Is it to the left? Is it to the right? It's an experimental value at any given point in time that shares the same expression as KEQ, but you insert any random concentrations to test whether you're at equilibrium or not. We refer to it as the reaction quotient. When Q is equal to K, we're at equilibrium. And if Q is bigger than K, it means we have more product than we should have at equilibrium. Hence, the system lies to the right of equilibrium and will shift to the left to return to it. If Q is equal to K, it means you are at equilibrium. There will be no shift. And finally, if Q is less than K, it means you have more reactant than you should at equilibrium, meaning your system is to the left of equilibrium and hence shifts to the right to return to equilibrium. And those are your three very, very important cases for Q versus K. Any questions on those? Okay. Third question type here, relating Q and K to determine equilibrium position and therefore which way you'll shift. So this is your quantitative way of determining whether you'll shift right or left. Basically, in these questions, you'll be given the concentrations of all substances at a given point in time. You'll be given a KEQ. And then you're asked to find the Q. Well, you won't be directly asked to find the Q, but you'll be asked to predict whether this is at equilibrium or not, or which side of equilibrium you're on, or which way you will shift. And it demands you to then use the concentrations to find a Q, and then compare Q and K as the steps you would take. So you can see here, the expression for equilibrium is here. They insert in the concentrations of everything from the question. Everything's divided by 2 because it's a 2-liter container to convert into concentration. You solve for a number, which is your Q, 1.4. And because that is so much smaller than 50.5, your KEQ value, your Q is less than K, and so your equilibrium shifts to the right, hence increasing the concentration of the products. Any questions there? Finding Q, comparing to K, figuring out are you shifting to the left or right. Okay. This question here is a good question to try. We didn't go through it in class when we went through this, but this question combines all of the, I guess, ice boxes with determination of equilibrium position. Just, I guess, bookmark this. There's an answer just below if you want to have a go at it. I'd recommend having a go. As we discussed, Q and K tell you about position of equilibrium, and there's factors that can change both Q and K. We are at equilibrium when Q equals K, and I like to visualize it as a number line. Shifting right means for your Q to get bigger. Shifting left means for your Q to get smaller. Q can be changed by concentration and volume pressure. So anything that changes concentrations changes Q and does not change K. Whatever happens to Q, say it increases, it will always return to K. It will always chase K. K, on the other hand, is only changed by temperature. So if you have a change in temperature in an endothermic reaction, K will increase, leading to equilibrium position demanding a higher product concentration and lower reactant concentration. And Q always chases K. K does not come back down to Q. In temperature change, the K moves and the Q comes back up to K until it's equal again at equilibrium. Okay. So this pretty much is the full picture. You know that LCP predicts shifts, collision theory explains the mechanism of shifts, and Q and K are your mathematical justification of whether you'll shift left or right. Okay. You then have two case studies. We'll talk about ionic dissociation in the fourth inquiry question. Ionic dissociation basically just being dissociation from an ionic compound, and the K expression you form is what we refer to as the solubility product, or KSP. Acid-base dissociation, which is Ka for acid dissociation constant and Kb for base dissociation constant, you can derive them from the expressions of an acid and base dissociating apart. And those are shown here. You just exclude water. Has anyone focused on acid-base dissociation constants much in school? Emily and Echo? Not too much? Okay, good. They're mod 6 anyway, so we'll see more of them next module. The final investigation here is your KEQ determination. So conduct an investigation to determine the KEQ of a chemical equilibrium system. For example, iron thiocyanate equilibrium. It's a very specific dot point. And as I said at the time, many schools teach it relatively poorly. Just out of interest as well, Emily and Echo, did you see this one as you went through 1.3 properly explained? Okay. So just to rehash it, colorimetry is a method where you are basically using light to find out the concentration of a colored solution. You're using light to find the concentration of a colored solution, and you need this for this KEQ method. The summary of the steps is you choose a color that's the complement of the sample that you're analyzing, because the complementary color is what is absorbed. So if your solution is orange, you're going to use a blue light, since blue will be absorbed. You then select a filter to get that light. So a blue filter will select for blue light, and by shining visible light through it, the only light that passes through the filter is that specific light you are filtering for. You then create this setup and set up a detector at the end. And the detector can calculate absorbance, which is how much light is being absorbed by the sample, where 100% of light exists before the sample, and then some smaller percent exists after. Say it might be 10% after 90% is absorbed. So your absorbance is defined as the log of the intensity before divided by the intensity after. And you don't have to do these calculations till mod 8. But basically, the more stuff, the more concentrated solution, concentrated, if it's more concentrated, this leads to a higher absorbance. If you have a more concentrated sample, you have a higher absorbance. So what you'll go and do is you get several standard solutions of known concentration, and you test their absorbances. You find that they form a linear relationship, and you can construct what we refer to as a calibration curve. Now, if you substitute this solution with any solution of unknown concentration, you can measure the absorbance, say it's 0.75, read across onto your graph, and you can find that it has a concentration that is now known from your calibration curve. Any questions there? Do I lose anyone at any of those steps? Happy to re-explain.
I was just wondering, like, the point of this experiment is to like find an unknown concentration.
Part of it, yes.
Yeah.
The point of this method here is to find an unknown concentration, but this is part of the method that allows us to find a KEQ.
Oh, yeah.
Does that make sense?
Yeah.
I'll put it in context now. This whole first bit is just a part of the KEQ investigation you do. And this comes in the next page. So this is the actual experiment, but that was background knowledge in order to do this.
Yeah.
So the experiment itself asks you to find the KEQ for iron thiocyanate. You'll take iron thiocyanate, which is a blood red species, and you'll need to use then a green filter to select the complementary color. Using standard solutions of iron thiocyanate, you can create a calibration curve, as we did before. So you would measure the absorbances of different known concentrations and essentially construct a calibration curve of iron thiocyanate concentration versus absorbance. Then what you'll do is you combine known concentrations of iron and thiocyanate. So it might be 0.1 molar of each, which allows you to create some iron thiocyanate solution of unknown concentration, because it will be a partial reaction. Not all of the iron and thiocyanate will turn into iron thiocyanate. That's the important part to realize for this step. Only say 50% converts or 60%, we don't know. Then by measuring that concentration of iron thiocyanate formed, this unknown concentration using your calibration curve, you now know the equilibrium concentration of iron thiocyanate. So now the concentration becomes known. And taking this all into an icebox, where Fe3 plus SCN minus and FeSCN2 plus, say this was 0.1, 0.1, and 0, and say that you found the concentration was 0.04 at equilibrium. Now it's as simple as solving your KEQ question from before. You find the change is 0.04 plus minus 0.04 minus 0.04, 0.06, 0.06, and you have all your equilibrium concentrations, allowing you to take this and put it into K. 0.04 and 0.06 squared. And you would get a K value from that. Does that make sense? Okay?
Yeah, it does. Thank you.
Okay. And everyone else, any questions? So if you do lose you anywhere along the way, we're all good. Gabriel, any questions? Okay. There's a final little bit on making iron thiocyanate standard solutions. Just be wary that it's not so simple as combining equimolar concentrations and expecting to get out a known concentration, because as we said, it's going to be a partial reaction only, not a complete one. So the way we get around that is by using a severe excess of one of the two ions. There's a mistake in the notes here. It should actually be of SCN minus and iron 3 plus being the part that's completely converted. This is important because iron 3 plus shows a orange color. So if you use that as excess, it may disrupt the colorimetry for the iron thiocyanate. So just make that correction and be sure to not mix those two up. Okay, and that's the end of the third inquiry question. KQ expressions, large versus small KEQ, Q versus K, your common KEQ calculations, the concept that Q always returns a K, and that Q changes from concentration and pressure, K changes from temperature. You have several applications through ionic dissociation and acid-base, and then finally the KQ experiment with iron thiocyanate and colorimetry to find a KQ. Okay. At the very end of all this, we have solution equilibria. I'll give you a quick 2-minute break this time, and we'll come back to finish this off and make it a little bit over time. Okay. Final inquiry question. We're doing well. Okay. So solution equilibria. As I said, Gabriel and Sophie, if you need to head off, no stress at all. But final inquiry question is on solubility, and we focus firstly on ionic compounds. So the first thing we discussed in this inquiry question was how does dissolution actually occur for an ionic compound? It comes down to 3 things: the breaking of bonds, which takes in energy, energy consumed, and then the making of bonds, energy being released. This balance creates an enthalpy change which can either be exothermic if you are releasing more energy than consuming, or endothermic if you are absorbing more energy than releasing. So that means for any ionic dissolution, you can have either endothermic or exothermic dissolution, and it really comes down to the entropy change being positive in most cases that causes the ionic dissolution to be spontaneous, because you're turning one solid mole typically into 2 or more aqueous moles, which are of higher entropy. So in the first stage, you break apart water's hydrogen bonds. That requires energy. In the second stage, you break apart the ionic bonds that hold together an ionic lattice. That requires energy as well. And the final stage is where you are forming ion dipoles. between the ions and the dipoles of water. This process, to be clear, is from the attraction of opposite charges, so electrostatic attraction, and the formation of what we refer to as hydration spheres, or hydration shells or solvation shells, where you can have 4 or 6 water molecules all around an ion in the middle, and that allows you to then form a release of energy from the formation of those bonds. And to summarize, ionic dissolution is favorable when you have a delta G that is less than 0. In order to have that, it's typically because your entropy is positive and your enthalpy can be either negative or positive, but it will be spontaneous when the entropy drive outweighs the enthalpy, if it is the positive case. Okay. A good summary table is here. Word of advice, the step up from year 11 to year 12, one of those steps up is that in your responses, you're often expected to draw diagrams, and they can actually request include a diagram, include 2 diagrams even. So in a dissolution response, to be very well prepared, I would take into the exam diagrams for how you draw hydrogen bonds between water, how you draw the ionic lattice, how you draw the ion dipoles in a solvation shell. And these would be what I'd take. Something like this to transfer into your question. Any questions on dissolution of ionic compounds? Okay. So then you understand how that works, how you dissolve an ionic compound, and we now have to relate it to mod 5. Mod 5 is all about equilibrium, and we then find out that all ionic dissolutions form equilibria, whether it's a static or dynamic equilibria. You will form a static equilibria in the case of an unsaturated solution, where you've dissolved a certain amount of solute, but it's not enough to make a saturated solution. It's not enough to make a saturated solution. That means the reaction went to completion. So you dissolved all of your solid, none of it is reprecipitating, and none of it is turning into dissolved ions anymore, because you've already removed all the solid. That's the case where you have a static equilibrium, a reaction that's gone to completion, 0 rate of forward and reverse reaction, and hence you can sometimes see dissolution shown with a single-ended arrow. That implies a complete dissolution. The case that's of more concern for us in Module 5 is the saturated case, where you add so much solute into solution that you can dissolve no more. This then will have an equal rate of dissociation and precipitation, where the ions are constantly going in and out of solution, going in and then coming out. This is where you then have an equilibrium system, shown with a double-ended arrow. The final case is supersaturation, where you actually have more ion in solution than the solution can hold. This can happen when you've heated or cooled a solution, dissolved more than you can at another temperature, and cooled the solution back down, for example. Or it's when you've mixed together 2 solutions that had ions in them, and when you mix the solutions, the ions now exceed the KSP, and so you'll be supersaturated. Whenever you have this supersaturated case, what will happen is you have the precipitation of those ions in order to return to just being saturated rather than supersaturated. You'll have the formation of a precipitate. And those are your 3 cases for solutions. They can be unsaturated, saturated, or supersaturated. Any questions there? Okay. one important case study from this inquiry question is the cycad fruit. The cycad fruit contains a water-soluble toxin called cycasin. You can remove it by dissolving it into solution. That whole process is a few steps where you strip the outer layer of the cycad fruit to get to the inner kernel, crush up that kernel to increase the surface area, and then you can go about this in then two ways. You can either perform this dissolution and removal of toxin in an open system or a closed system. What would be the two ways you can remove this toxin? How would you do an open system or closed system? How are they different? How can you remove this toxin in an open system? And then how could you remove it in a closed system? If I put it into a bucket filled with water and then let the kernel just have all of the toxin dissolve out, is that an open or closed system?
A closed system.
It's a closed system. So at some point, if you try to do this method in a bucket, you're going to reach a point of saturation, unless you're only a very small amount of toxin. You reach a point of saturation and you can form a dynamic equilibria. You would then, once you have all this toxin in the solution, you can remove that water containing toxin to shift equilibrium right and hence dissolve more toxin into the solution when you replace it with new fresh water. The other variant for this method is talking about dissociating in an open stream. So if you have a running stream of water and you have this same toxin in the middle, the stream is going to remove matter from the system continually. The matter will just be removed at a constant rate, hence continuing to shift the equilibrium right. Matter is removed, equilibrium shifts right, and you continue to dissolve all this toxin in the stream until it's all gone. So just be wary when you justify this, that you know when you talk about dissolving into a bucket of water, that's a closed system and you justify it as that. And if you're talking about the stream, you're forming an open system and you are continually shifting equilibrium from the removal of matter. And be wary of that as well. Any questions on those two?
Yeah, sorry. With the cycad, like the steps to detoxifying it, do we have to like know those? Would they ask us a question like, how did they take out the toxins?
4 marks. Exactly that question.
Okay, so we should just memorize those steps.
Correct.
Okay.
Yes. So it'd be 4 marks. They'd say, explain how Aboriginal and Torres Strait Islander people remove toxin, use solubility equilibria to remove toxicity from foods. And you just dump this whole thing. It's like the same question every time, and it's 4 marks, which once you have repaired, you'll get for the rest of this year. But I doubt your school would ask it more than once throughout the year if they're writing good papers. And I think you go to Redham, is that right? Yeah, Redham, from my understanding, writes pretty good papers. Okay. Solubility rules and precipitation. Hopefully, by this point, you've come up with a system to remember your solubility rules, whether it's NAG, SAG, PMS, Castro-Bear, or you're manually remembering, it doesn't really matter. Just have a system that works. If you wanted to investigate solubility rules and find certain ones, you can show whether precipitates form or not when you combine high concentrations of 2 ions together. So if I had a solution of magnesium and a solution of, let's say, magnesium's not a great one. Let's say it's lead, and then I have chloride ions, and I combine the 2 solutions together, and I form precipitate. It means that those 2 substances that compound is insoluble in water. There are 3 case studies for precipitations, but I would say that these are not like overwhelmingly rote learning. They kind of just as an example to show that you can precipitate these substances together. You can find out that these would precipitate from the solubility rules anyway. Okay. Final thing we'll talk on today is KSP, QSP, and common ion effect at the very end. So KSP, as we know now, is a subtype of KEQ, and it's only specific for ionic compound dissociation or dissolution. KSP is derived from a solid dissociating to two or more ions, and the KSP expression does not have a denominator because the reactant is solid. The first question type we get is molar solubility, finding out how much of a solid we can dissolve per mole of solvent. This is basically finding at what point the solution becomes saturated, and you can be asked it in that way. Instead of being asked calculate the molar solubility, you can be asked for calculate the concentration once the solution becomes saturated. It's the same question. And it's in terms of moles per liter, molar solubility. Steps to finding molar solubility from KSP. Very, very standard, repeatable question. You would basically write your equation. So the question would be calculate the molar solubility of barium hydroxide. You write your equation for the dissociation. There's a small mistake here. It should be 2OH. Apologies. You would assume X is the amount of barium hydroxide that can dissolve in 1 liter. Therefore, the change in barium and hydroxide concentrations are in terms of X, being X and 2X. Putting them into KSP, you would then find that you can equate that expression with the KSP value, which you can find from your data sheet. And once you solve for X, you have the concentration, like the moles per liter of barium hydroxide, which is represented by X, that you've dissociated into solution as 3.99 times 10 to the negative 2. And that's your molar solubility. So first question type, relatively standard. Just be wary, like the common, I guess, things you see are like x squared, 4x cubed, I think it's 27, x to the 4, and like 108, x to the 5, I think, are the most common variations that you'll see. So just be careful of those. All right. Cool. So QSP, similar to QEQ, it's just a experimental value. It gives you a guide as to where you are at equilibrium. Are you to the right of K, to the left of K? And that means are you saturated, unsaturated, are you supersaturated or are you unsaturated? So if QSP is less than KSP, this means that your solution does not yet have the concentration required to be at the point of saturation. You do not have the concentration required to be at the point of saturation yet. And hence, this is an unsaturated solution where you could still dissolve more ionic solid. It's important to note that QSP is slightly different to QEQ in the sense that if your QSP is less than KSP, it will not increase up to KSP. It just stays. Unless you add more solute. In that case, your QSP can go up. In the middle case, if your QSP is equal to your KSP, your solution is saturated and you are at equilibrium, exactly. And your QSP remains constant. In the final case, if your QSP is greater than KSP, it means you have more ions in solution than the solution is supposed to be able to hold, meaning your solution is supersaturated and an ionic solid will precipitate in order to bring QSP back down to KSP. So the two common question types you'll get around QSP. Question type 1 is, will a precipitate form when you combine two ionic solutions? And the easier version of this is you just have two ion concentrations, will a precipitate form? That skips the step of combining solutions, but typically it's from combining solutions. So you have a volume of one solution, you have a volume of another solution, concentrations are given. The first step is finding the new concentrations after the dilution occurs, because if you're combining concentrations, you're going to be diluting the two solutions. Then once you find those concentrations, you find the QSP expression, insert those values in, and find your QSP. Then you do Q versus K, which allows you to find, in this case, if there's no precipitate, Q was less than KSP, and hence you are unsaturated. Any questions on this question type? Cool. And the final thing we'll talk about for the term is common ion effect. Common ion effect is where you try to dissolve a salt in a solution that already contains one of the ions that would be formed. So solubility is decreased compared to dissolution in pure water. From an LCP standpoint, you can justify it. From a QSP standpoint, you can justify it. But that's the effect in summary. Okay. The calculation you'll see over and over again is they'll ask you what's the solubility of a substance, say silver phosphate, in a solution, silver nitrate, that shares one of the ions in the substance you're trying to dissolve. In this case, they actually do a comparison. They do a molar solubility of silver phosphate in water first. So this is the molar solubility in pure water. And then this second part of the stem is a common ion effect. And this nicely shows that when you have that common ion, the concentration will end up being lower for the molar solubility. So in silver nitrate solution, assuming that silver is 0.1, and I'll show you what they mean by this in terms of an ice table. So silver phosphate Ag3PO4 would associate into Ag plus 3 of those and PO4, ICE. So assuming that you have 0.1 mole per liter of silver nitrate to begin with, this means that the number you insert here is 0.100 mole per liter. Your silver phosphate, you suppose, is X. Once again, that's the maximum silver phosphate I can dissolve in this scenario. So then your changes are minus X plus 3X and X, 0, 0.1 plus 3X and X. So if you want to solve this for KSP, you could try processing this, but you'd end up with a quadratic. So as we know now, our workaround is applying small change assumption. Because the KSP is 8.89 times 10 to the negative 17. 10 to the negative 17. It means that we can assume 3x is negligible. And this is the calculation they do below here. They do 8.89 times 10 to the negative 17. Your KSP is equal to 0.100 cubed times by x. And they can solve for x being 8.89 times 10 to the negative 14. And that's common ion effect. If you compare the concentration in water, the molar solubility, versus the concentration in the common ion solution, you can clearly see the common ion molar solubility is much, much lower. Does that make sense for everyone? Common ion effect. Your calculations will pretty much always just be a small change assumption icebox with common ion effect. Okay. And that brings us to the end of content session 4. We talked through dissolution of ionic salts, finding spontaneity for dissociation, how dissolution forms equilibria in unsaturated, saturated, or supersaturated solutions, the cycasin case study, the cycad fruits, the solubility rules, ionic dissolution, KSP expressions, QSP expressions, molar solubility, how to find it, QSP, what it means when you compare it against KSP, and finally the common ion effect, and how you calculate it using small change assumption for molar solubility. And so that is the end of the 4th content session, the end of Mod 5, and hopefully on a second run through that makes a lot more sense for all of you. Okay, so that's the end of the session today and the end of the official Catalyst term, the term 4. You've all done very well. You've gone through your first paper already, and hopefully you feel that you have come a long way, because I can tell you all have. All that's left from now to your exam is a lot of practice questions. I would spend no longer on revision of content unless it's a discovered gap and you come back to revise it. I would spend all of your time for chemistry from here on out just doing questions. That's the highest leverage thing you can do. As I said, for next week, there'll be drop-in sessions. So if you have questions you struggle with, and the best students turn up to these sessions with a fair few questions and we just pump through them back to back, come along, ask your questions, hear other people's questions too. That's one of the best ways to learn. And those will be scheduled throughout. So just keep an eye out. I'll post the times in the classroom and probably send a text message as well, just so you have those times. And if there are any questions in the meantime, don't hesitate to send it on the classroom or the academics email. We've got team members monitoring that around the clock. So I'll let you all go. If you have any final questions, feel free to stay behind. But otherwise, that's all for this term. And see you potentially next week. And if I don't see you, best of luck for your exam. And let me know how it goes after. See you soon.